We're down to the last application of derivatives. This is section 2.9, differentials. Let's consider this straightforward task. Approximate the square root of 3.96. The calculator output is 1.98997. But have you ever wondered how calculators and machines can easily approximate expressions such as the fifth root of 7 or the sine of 47 degrees? They don't even have to give the exact value. An approximation that matches the number of decimal places that can be displayed is enough. What's the mathematics behind this? In this section, let's use calculus to approximate the square root of 3.96. Equivalently, we want to approximate f of 3.96, where f is the square root function whose graph is shown. X equal to 3.96 is close to x equal to 4. The square root of 4 is 2. So it is reasonable to assume that f of 3.96, or the square root of 3.96, is close to the number 2. Here is a zoomed in portion of the square root function. Shown there is 4, 2, and the other point has x-coordinate 3.96. We're interested in approximating the y-coordinate, assuming that we don't have any calculator available. Draw the tangent line at x equal to 4. That's the purple line. The point on this tangent line, where x is equal to 3.96, is the purple point. Before you continue, find the equation of this tangent line. Pause the video. You should have gotten y equal to 0.25x plus 1. I labeled it as L, so that's the equation of the purple tangent line. Notice that the y-coordinate of the purple point is close to the y-coordinate of the green point, with the latter being the actual square root of 3.96. This is the actual square root of 3.96, but this is not so far from it. Furthermore, y-coordinates from the purple linear function are easier to compute because you just have to plug in 3.96 in place of x here, multiply by 0.25, and then 1. Let's go back to the other window. L of 3.96 is equal to 0.25 times 3.96 plus 1 equal to 1.99. Because L is a linear function, only the 4 basic operations are involved. Here we used addition and multiplication, in fact. We now have the approximation to the square root of 3.96 as 1.99. This is because we used L of 3.96 to approximate f of 3.96, which is the square root of 3.96. Our basis for this being the fact that if x is close to 4, such as in the case of when x is 3.96, then the y-coordinate of the point on the square root function's graph and the y-coordinate of the point on the tangent function, these are not going to differ by much. Now for our next example, let's use what we've learned to approximate the square root of 4.2. This time, we're also going to use a linear approximation, in other words, the equation of a tangent line. Note, however, that just like 3.96, 4.2 is close to 4, which means that we can use the same tangent line. L of x is equal to 0.25x plus 1. So L of 4.2 is 0.25, with x replaced by 4.2 plus 1. The result is 2.05. So therefore, the square root of 4.2 is approximately equal to the following value, 2.05. If you compare this to 2.04939, the calculator output, which is of course better, but when rounded off to 2 decimal places, Our answer of 2.05 is correct. Now next, let's approximate the square root of 9.5. Now the difference this time is that 9.5 is subjectively much farther from 4. So the operation or the function suggested here is the square root function, but 9.5 is much farther away from 4. And the farther the value of x is from 4, then the farther the values of f of x and L of x are going to be from each other. So for example, if you trace this green point on the square root function and you compare that to the corresponding point on the tangent line, they're getting farther and farther away from each other. There's a widening gap between their y coordinates, so which means that using the y coordinate of the corresponding point on the tangent line would not produce a robust estimate to the y-coordinate that we're actually interested in, which is on the original functions graph. So we can't use the same tangent line, is all we're saying, but since 9.5 is close to 9, then that means what we gotta do here is use the tangent line to f instead of at 4, but the tangent line at 9. Now pause the video to find the equation of this orange tangent line shown in the graph, tangent to the graph, the square root function at 9, 3. Did you get the same function L of x equal to 1/6 of x plus 3 halves? So this is the tangent line at 9. So therefore, L of 9.5 would be a good approximation to the square root of 9.5. So simply plugging in 9.5 in place of x here into this linear function will result in this 3 decimal place approximation, 3.083. It would be interesting to see what the calculator output is. It's 3.082207, which when rounded off to 3 decimal places is consistent with our linear approximation. Use a linear approximation to estimate 16.2 to the power 3/4. What function is this suggesting that we use? Did you conclude the same function, f of x equal to x to the 3/4? So what we want to estimate is therefore f of 16.2. Now 16.2 is close to 16, which is a convenient number as far as this function f is concerned, because 16's fourth root is equal to 2. We therefore want the tangent line to this function f at 4. You can pause the video now to find its equation first. Alright, did you find the equation of the tangent line? So the ingredients that we need, which I did not show in detail in the previous exercises, but now I'm doing it, f of 16 equals 8. The derivative is something we need, 3/4 of x raised to negative 1/4. The slope of the tangent line is therefore f prime evaluated at 16, which is 3/8. So therefore the equation is y minus 8 from the point 16, 8. And then the slope is 3/8, and then x minus the x coordinate 16 of the point of tangency. If you solve for y, you're going to get 3/8 of x plus 2. Let's label that linear function L. L of 16.2 is 8.075. Our approximation to 16.2 raised to the 3/4 is 8.075. The calculator output is 8.07488. Quite close. Now the name of this section is differentials. What are they and how are they used in approximations? Recall the earlier task of approximating the square root of 3.96, which is f of 3.96 if f is the square root function. 3.96 is close to 4. So the square root of 3.96 should be close to the square root of 4, which is 2. Now these observations can be described by imagining that the value of x is changed from 4 to 3.96. The change in x, denoted by delta x, is the new x value 3.96 minus the old x value 4. So delta x is equal to negative 0.04. Y should also change from 2, but to what? We can also denote by delta y the corresponding change in y, the unknown y value minus the old y value of 2. If we can figure out by how much y will change, we can use this to determine what the new value of y will be. We will now define two new quantities. Shown below is the graph of some function f. P is the point on the graph corresponding to a particular value of x. Suppose x changes by delta x. Let q be the corresponding newer point then on the graph of this function f, the purple graph. Let delta y be the change in the y coordinates. Delta y and delta x don't have to be positive. Now, the first of the two quantities that we're going to define is the differential of x, denoted by dx. dx equals delta x. By definition, they are exactly the same. Draw the tangent line to the graph at the point P. Let R be the point on this tangent line after changing the original x value by delta x. So if the new x value is x plus delta x, then on the graph of f, the corresponding new point is q. On the tangent line, the corresponding new point is r. The differential of y is then defined to be the amount by which the y-coordinate from P to R is changed. This corresponds to how delta y is the amount by which the y-coordinate from P to Q is changed, and then the amount by which the y-coordinate from P to R is changed is what the differential of y represents. But how can we compute dy? Consider the slope of the tangent line at P. What's the slope? The slope is f prime of x. However, this is also the slope of the line from P to R. And from high school algebra, that's merely the rise over run. The rise or the vertical change is dy, while the run or horizontal change is dx. Therefore, f prime of x is equal to dy over dx. Solving this equation for dy allows us to define the differential of y, which is dy, as f prime of x multiplied by d of x. By definition, let's compare the two differentials. By definition, the differential of x dx is delta x. On the other hand, dy, this blue dotted segment, and delta y, this black solid segment, they are different. But if dx or delta x is close to 0, then both q and r would be much closer to p, and consequently q and r would be much closer to each other. The vertical segments with lengths delta y and dy would then be much closer in length. Thus, dy will be approximately equal to delta y. We can use dy, defined as f prime of x dx, to approximate delta y, the actual change in y. So let me repeat that again. If dx equals delta x by definition is small, meaning close to 0, then dy is an approximation to delta y.